Thank you. It's nice to be here. So I want to talk about a couple of experiences we had recently in StarkWare for implementing modular arithmetics over some fields inside different fields, and a little bit about the techniques and tricks that we use to do that. So it will be a bit technical at some points. Right, so first off is we have a big field and we want to put an even bigger field inside that big field. So more specifically, we have a stone prover. This prover proves Cairo programs by compiling them into a Stark. As probably all of you know, Stark proves validity of an algebraic intermediate representation, which is a list of polynomial constraints on the trace of a computation. And both Cairo and this that the Stark proves have a native register type, which is a field element, which we call felt, over a big prime, which is roughly 2 to the 251. Cairo allows us to use basic operations called Cairo steps, and they include things like field arithmetic between elements on the stack. So one element can be the sum of different elements on the stack or the product of different elements on the stack. So we can have memory access. So one element on the stack can be a pointer to another element on the stack, and we can dereference that pointer. And we have program flow depending on elements of the step, whether to go to this instruction or a different instruction. So all of these things together are Turing complete, but you can do anything using these kind of steps. But it can be very expensive to do certain things only using field arithmetic. Each one of these steps has a fixed cost in number of trace cells, and we want to minimize that cost to have shorter proofs, to have cheaper prover time. So for that purposes, some operations we allow using built-ins, which implement some of these operations directly by polynomial constraints instead of using the Cairo steps, which are then turned into polynomial constraints. So for example, range checking, as was just mentioned, can be such a built-in, just direct polynomial constraints. Bitwise operations, you don't really want to do bitwise operations using field element operations, but you can do it much cheaply just with polynomial constraints on certain elements. Similarly, computing hashes can be very inefficient if done directly in Cairo, but can be much more efficient directly on the air. And all of these things are then given access to the Cairo programmer, can use these built-ins with minimal interaction between Cairo steps and the built-ins. So one example of a thing that we want to do is to allow field operations in other fields other than our native Cairo field. For example, for computing elliptic curve operations for cryptography on curves such as BN254 or SECP or BLS12381. All of these are in Feltoid's Garga library. And the general idea for how to do this kind of arithmetic is to break down these big field elements into limbs that will fit in a felt. And actually, we want products of such limbs to also fit in a felt. So each of these limbs should have size which is at most half the size of a felt. And then we can use these limbs to simulate modular arithmetics. So we want to support here fields up to 384 bits. We know that's useful for that BLS curve. So we decided to use 4 limbs of 96 bits each for this built-in. And all of this decomposition, again, can be done in pure Cairo, but again, it will be very inefficient to, you have a lot of constraints here between these limbs to simulate this arithmetic, much more efficient to do it as a built-in. And this built-in is also very different from the other built-ins that we have. So for example, for range check, how will the user use it? They just provide an input to this range check built-in, and then they know that this thing will be in that range. For bitwise, you provide inputs and you get outputs. It's very direct, very low communication. Here we don't have something similar to that. The interface is not that the user provides A and B and M and gets as output A plus B modulo M. The reason not to do that is mostly that even this communication is very high. So each of these A, B, and M, as we said, it's 4 field elements in itself. So just writing these things down for the built-in and then reading the output from the built-in, all of this already takes a lot of Cairo steps in itself. And it's not the common use case. You don't usually just want to do one operation modulo M. You usually have a bunch of operations modulo the same M. You usually have circuits. For example, if you want to do elliptic curve operations, then each one of those involves a lot of predefined steps of repeating the same kind of operations in that field. it's much more efficient to build that circuit, provide the entire circuit to the built-in, and then get the output of a circuit. So the way the interface actually works is that the Cairo programmer provides the modulus M, which is fixed for the circuit, a pointer to the list of all the values that will be the intermediate values used in the circuit, including pre-filled the inputs that they need, and two arrays of triplets. Each one gives us offsets to either an addition gate or multiplication gate. So triplet ABC, which says that either the value at A plus the value at B is equal to the value at C modulo M, or the product is equal to that. Using these kind of gates, you can also get subtraction and division. You just have to give A and C to be the values that are already known, and then B is derived to be the division or subtraction, depending on whether it's a multiplication or addition gates. And the programmer provides all of these things to the built-in, and the built-in then automatically fills in all of the values in the, all of the missing values in the values, including the outputs that the programmer can then access or assert other things on, and enforce everything with polynomial constraints. And so getting a bit deeper into the arithmetic, how do we actually do the arithmetic inside these modulo built-ins? We want to verify that op AB is C plus some multiple of the modulus M, where op here is either addition or multiplication. For addition, we only need to add k, which is either 0 or 1, assuming A, B, and C are all between 0 and the modulus. So either A plus B is between 0 and modulus, and then k will be 0, or it's over the modulus by at most m, so k will be 1. And for multiplication, k can be as large as the full capacity of these limbs. Technically, it can be at most m, but we don't know m in advance, so m can be as large as 2 to the 384 generally. How do we verify that? We shift everything to one side, and we compute that this thing is actually equal to 0 by computing it limb by limb, and observing the carries and writing constraints down on the carries. So what it actually means to compute it limb by limb is that for every limb, we see that the ith limb of op AB minus the ith limb of C minus the ith limb of k times n plus the I minus 1 limb from the previous carry should be the next carry times our radix, which is 2 to the 96. And this should hold for every I. We have 4 of these constraints for addition, 7 of these constraints for multiplication. Right? 3 plus 3 is 6 plus 1, because you start from 0. And we also need to constrain that these carries are in the proper range, and this range is plus minus 1 or 0 for addition, because everything here is just small limbs. And it can be up to slightly larger than 2 to the 96 for multiplication. Why is it slightly larger? Because the ith limb of A times B, or of K times M in that case, is actually not just bounded by 2 to the 192, it's actually a convolution of the product. So for example, the third limb of A times B is actually A3 B0 plus A2 B1 plus A1 B2 plus A0 B3. So it goes up to 2 to the 194, which is 2 times 96 plus 2. So that epsilon is equal to 2, in fact. All of this we can save a little bit on these constraints by using polynomial evaluations and interactions. So every element that we have here, which is written as sum of limbs times powers of a radix, we can consider a polynomial that matches it with the same coefficients. So from the polynomial, you get the element back by just plugging in x equals to 2 to the 96. And we notice that this constraint star on the carries that we had for each I is actually a constraint about coefficients of a certain polynomial that's written there, which is op ax bx minus cx minus kx times mx, plus this interesting thing, x minus 2 to the 96 times carry. And this multiplication by x exactly gives us the shift by 1 that we have from the carries, that we get the carry from the previous one. X times carry x, the ith coefficient of that is carry I minus 1. So the condition star is exactly equivalent to this polynomial vanishing by coefficients. On the other hand, we know that it's a very low degree polynomial. It's degree 3 for addition, degree 6 for multiplication. And our field is very large. It's size 2 to 251. So to prove that this polynomial vanishes, we can sample it at a random verifier provided point. And if that vanishes, then almost surely this polynomial actually vanishes in all of its coefficients. And we can save some constraints. So instead of having the 4 or 7 constraint we said, it's just one constraint, but with interaction. And actually, for multiplication, this also saves us a few multiplication operations, because we don't have to compute the entire convolution that we mentioned before. We just have to evaluate A and B at points X, and then one multiplication of field elements instead of 16. And same for K and M. Evaluating is also 8 multiplications, but it's still a nice saving in the number of multiplications that we have here. So this is how to do multiplication for our bigger field inside big field with some nice tricks. And this trick also helps us for addition, and not only multiplication, this polynomial evaluation trick. So that was the first issue and the first item. And the second one is simulating a big field inside a much smaller field. Our next use case is we are now working on STU, our next generation prover, which will be for a circle Stark over base field M31, Mersenne, the 31th Mersenne number. And from now on, for the next 2 slides, felt will mean field elements inside this smaller field. We use a smaller field because it gives us much faster proving time. Operations in this field are much, much faster than operations in a big field in terms of CPU and so on. But problem, we already have StarkNet exists. It uses Cairo, it uses Stone. Existing programs already rely on the fact that the field is 2 to 251. We can't just abandon it and say that the field is actually 2 to 31 minus 1 and everything will work the same. It won't work the same. So we have to support also the existing things that currently exist. So we need STU to also support operations over this specific finite field. It's very important. We'll call the field elements of that field felt 252 to distinguish them. And what we know is this P is now fixed, unlike in the modulo built-in that we discussed before, which we wanted to support for general moduli that we don't know in advance. This P is fixed, it's known, and it's also very sparse in bits, which is a part of the reason why it was chosen originally. We see that it only has 3 powers of 2 here that appear at all, and with a small coefficient there. And we will take advantage of that property of P to make the multiplication specifically more efficient. So the sparseness of P actually means that modulo P, some powers of 2 will also be very sparse. So how do we compute a large power of 2 modulo P? We can see that the fact that P equals 2 to the 251 plus 17 to the 192 plus 1 means that modulo P, 2 to the 251, is minus 17 times 2 to the 192 minus 1. And if we multiply that identity by a power of 2, but not too big power of 2, then we get that some powers of 2 up to P are just sums of minus 17 times the power of 2 minus 1 times the power of 2. And similarly for negative powers, we get from the original definition of P that minus 1 is equivalent to minus 2 to the 251 minus 17 times 2 to the 192. And if we divide this by a power of 2, then it will be just the same as if dividing 1 by this power of 2 will be the same as dividing the 2 other powers of 2 by powers of 2, and they will remain positive numbers of 2 for a small enough C. So just as before, we want to break down our large field element into limbs that will fit inside the smaller field element. We use 28 limbs of 9 bits each. And the reason for this particular numbers will be specified very soon. And we want to make sure that the coefficients that we get here in terms of these limbs are small, and for that we multiply by minus 4. So after multiplying by minus 4, and we write everything down now in terms of this radix of 2 to the 9, so all of the exponents that you see in these 2 lines are divisible by 9. 189 is divisible by 9, is the statement. We get that -4 times a power of 2, which is above 252, is equivalent to exactly the same formula that we had above, multiplied by -4. The 193, we took 16 out to get 189, which is divisible by 9. And we break down this 17 times 64, which is a number which is bigger than 512, our radix. So instead of getting one limb with a very high coefficient, we get it as two adjacent limbs, the b plus 22 limb and the b plus 21 limb, with coefficients 2 and 64. And similarly, in the negative powers, we have that 17 times 32, and that breaks down into the 1 times 2 to the 9, 22 minus c plus the 32, 21 minus c. And you can see here the reason that we had to have the -4. If we had, for example, -2 instead of -4, then that coefficient of 2 to the 9, 22 minus c would have been half instead of being 1. But half means that it actually goes back to the previous coefficient with a coefficient of more than 256. It would have been 272 together with that half of 32. And that's a much bigger coefficient than the maximal coefficient we have here of 64. Similarly, if we divide it by 2 again, then the coefficients of 2s that we see here in both lines would have become halves and given us very large coefficients. So we played around a bit with these options, and we found that having limbs of 9 bits with this coefficient gives us relatively low coefficients in this kind of forms, and we see that we want these things to actually be reduced modulo p, so we want them to fit inside our 28 limbs that we have, and that is the case when b is between 0 and 5 for the higher powers, and when c is between 1 and 21. So we see that the b plus 22 element means that b cannot be bigger than 5. The 9b element means that b cannot be negative. Similarly, 28 minus c says that c should be at least 1, and 21 minus c says that c should be at most 21. And the nice thing is that this gives us 27 more elements, which is exactly what we need. So the full algorithm of how we apply this thing is we first compute a times b minus c formally. So each of these xi's are actually from the convolution of a times b, and some of them have the minus ci parts. The sum goes here from 0 to 54 inclusive, which is 2 times 27. So some of these xi's can be very large. The middle one will be a sum of 28 products of limbs of size 9 bits, so it can be as large as 28 times 2 to the 18. After we computed that convolution, we multiplied by -4 times 2 to the minus 189 and reduced modulo p. So, but first reduction is done by taking that coefficient, plugging it into the coefficient of the limb, the 2 to the 9 I part, and reducing that modulo p exactly by these formulas that we have. So for I, which is between 21 and 49, we just get that these are limbs inside the range of 0 to 27 by themselves, or 28 not inclusive. And for i's which are less than 21, we get that these are negative powers which fit into this formula with minus 9c. And for i's which are greater than 49, we get that these are positive powers, but exactly in the range that fits into this 252 plus 9b without overflowing. And each one of these things in this range will give us, will match with 3 of these yj's that we have. So each yj will be the sum of a few of the xi's with some coefficients that we got from those formulas. Some of these xi's will contribute to 3 yj's, some of them will contribute to a single yj. On average, it's about 4 x's per y. After we get all of these y's, again, they're not reduced, they're just formal sums with these coefficients. We want to finally show that this sum is 0 modulo p, that's the whole thing, that A times B minus C is 0 modulo P. So we need to find the coefficient K of P that will give us this formula. And actually, this coefficient will be very small. It's about as small as the Y27 coefficients divided by 2 to the 10, which is less than 2 to the 18, which is very nice. It definitely fits inside a felt, inside an M31 element. And after we have that K, we just prove everything by constraints on the carries, exactly as we had in the mod built-in, without here the trick of polynomial evaluations, because actually here the degree is not that small, and the field size is not that large. So the soundness of evaluating on a point here inside the field will not be as good as it was for the bigger field. And the cost of writing down these constraints is also not that high on the other end. And as we said, the parameters for 28 and 9 were chosen exactly so that all of these things together with the coefficients, with the reductions, we don't get any overflows of the 2 to the 31 field. So it actually all fits together. It doesn't even overflow 2 to the 28, if I'm not mistaken. And that's it.